Денис, привет. Видно все в зуме?
Доброе утро, да, все видно.
Давай сейчас подождем там. Давай. Меньше.
А запись нет?
Не знаю.
Нет. А, вот есть. Все.
А это что, работает штука?
Нет, мы же выделили. Мы же...
Мышка, да, хорошо.
Нажать мышкой на экран, чтобы выбрать PDF, и нажать Ctrl, чтобы перейти в режим показа. Вот, да. Just to not appear. It's necessary to have also. So beautifully, you're right. It's just
А почему не видно у меня название доклада?
А это вот
Так будет, да?
подождите, вы нажмите дополнительно, вот эту штуку перетяните.
Вот это?
Да.
Не,
Название
не
видно
мешает.
наверху
Нет,
голубым
дополнительно.
текстом.
Это не мешает.
Theory and application of
Что-то
Siegert
дополнительно.
states.
И
Нам
скрыть
видно.
перемещаемый элемент, вот этот третий с конца.
Так.
This is the noise. You should do something. Yes. Okay, together.
Population. Then add a small perturbation. Is confident to this prevented to this population. Yeah. Okay, let's start. Misha, do you hear us? Well, I mean.
Да, я очень хорошо вас. I hear you well.
Today we have our own
Can see
speaker,
you well.
Professor Oleg I Tolstikhin, who will speak about something interesting for me in particular. So about Siegert states, theory and application.
Okay, thank you. So I will present a review of results available in theory of Siegert states and illustrate some of its applications. And first of all, I have to say that this talk is motivated by a question asked by Volodya during one of my previous talks here. And that is why I begin with some history of the subject. So in his famous paper of 1928, Gauss developed the theory of radiative decay. And in the derivation, he introduced two important analytical advances which were new that time. One is he introduced complex energy, which I will discuss now. And the second, his contribution, new contribution, was the semi-classical treatment of tunneling through the barrier. So he was the first to apply double KB or semi-classical theory, which was developed at that time to the problem of tunneling through a barrier. I will not discuss this second contribution because it has nothing to do with the subject of my talk, but the first one I will discuss here. So he considered such a one-dimensional potential with two potential barriers. And he felt that to describe radiative decay, one must impose outgoing wave boundary conditions. These two equations show that to the right of the right barrier, we have only outgoing wave going to the right. And to the left of the left barrier, we also have only outgoing wave, a wave going to the left. Then he realized that if we try to find a stationary solution to the Schrödinger equation with such boundary conditions, and if we integrate a continuity equation over the region occupied by the potential, that is from the left to the right sides of this barrier, then we get a contradiction if the energy of the stationary state is real. If the energy of the stationary state is real, then the probability for a particle to be within this interval does not vary with time, so this time derivative vanishes. But on the other hand, there is flux going to the right and to the left. So this right-hand side, which originates from the divergence term in the continuity equation, is non-zero. So to resolve this contradiction, he suggested to make the energy of the stationary state complex. And then if the energy becomes complex, then this can be satisfied. So he realized the fact that a stationary solution to the Schrödinger equation satisfying purely outgoing wave boundary conditions at all boundaries available in the problem cannot have purely real energy. It must have complex energy. So this is his contribution to the subject of Siegert states. I want to emphasize that even though this is a very important step, realization that the energy must be complex, he thought about just one single solution of the Schrödinger equation satisfying these outgoing wave boundary conditions. He did not think about a complete set, which I will focus on later. And then he applied this argumentation to this tunneling through a barrier problem and obtained his famous result, which reproduced the experimental Geiger-Nettel law for radiative decay of a nuclei. So this paper, in a sense, is important. At least certainly it should be mentioned in the review of the theory of Siegert states, but here he considered only one state. In 1936, Bright and Wigner suggested what is now known Bright-Wigner formula, which describes the profile of resonance in scattering of. They applied this to the explanation of peaks, resonance peaks in scattering of different nuclei, in internuclear scattering. And they derived this Bright-Wigner formula, which is now called Bright-Wigner formula. In first years after they suggested this formula, it was called dispersion formula, because they derived this Bright-Wigner formula using time-dependent perturbation theory. Something similar like how the dispersion formula for example, for polarizability of an atom is derived using perturbation, time-dependent perturbation theory. And this was not satisfactory derivation because there was no small parameter. Resonances are very narrow, very strong. The intensity in that resonance scattering is very strong, so there is no arguments to justify application of perturbation theory, and many authors were interested to how to derive Bright-Wigner formula from the Schrödinger equation without applying perturbation theory. So the first who tried to do this were these people, Kapoor and Parles. Parles, I hope you know this name. They suggested the following. Suppose we have energy of collision particles. So particles like one nuclei collides with another nuclei. This is the collision energy in the center of mass frame. This is fixed. Let's impose this outgoing wave boundary condition at some boundary or distance between the two nuclei, where K is related to the energy by this equation. Then they suggested to consider the following eigenvalue problem. Here, energy acts as an eigenvalue which should be found, but this eigenfunction must satisfy this outgoing wave boundary condition with a fixed energy E. This energy E and these eigenenergies Wn are different things. This is fixed, and this defines the k in the outgoing wave boundary condition, while this should be found by solving this eigenvalue problem, this plus this. So the problem with this set of yes, and they
What is potential in
potential is some potential which describes here we talk about S wave scattering in a central potential. Like in that time, people thought about collision of two particles interacting through this central potential. This is any potential.
I mean, because of this potential, E doesn't equal to W.
Not because of this potential. Potential is necessarily present in this equation because we want to treat some collision governed by the potential. But what they suggested, a set of states that they introduced, is defined by these two equations. And I want to emphasize here that K, which stands in the outgoing wave boundary condition, what does this mean? That at the boundary of the region occupied by the potential is assumed to be finite range. At the boundary of this region, logarithmic derivative of the wave function is a constant equal ik, where k is determined by a given collision energy. So this energy is fixed. They notice that if we supplement this Schrödinger equation with this boundary condition, it becomes an eigenvalue problem. So eigenvalue problem for this quantity, for Wn, which is denoted by Wn. And the problem, I mean, the deficiency of this approach is that, okay, you can introduce such a set, but the eigenvalues and the eigenfunctions depend on this energy as an external parameter. This energy should be fixed to define this set. So this was 1938, and in 1939, motivated by the same reason to derive Breit-Wigner formula from the Schrödinger equation, Siegert introduced another eigenvalue problem, which is slightly different, but actually this small difference is very essential. Here is the same equation as I showed before. So it's a radial equation describing scattering in a given S wave scattering in a given potential. This is regularity boundary condition at r equals 0. This is outgoing wave boundary condition at the boundary of the region occupied by the potential. But Kn, which appears in the outgoing wave boundary condition, now is determined by the Wn, which is eigenenergy of the state, which appears in the Schrödinger equation. Now, this quantity and this quantity are related. So you can say that this Wn is k squared over 2. While in the Kapur-Piles approach, this energy depended on this energy as a parameter, as external parameter which you have to fix. This problem became in some sense self-consistent. There are no external parameters in this formulation. So this is the first important achievement by Siegert. But the second achievement is that he analyzed some properties of these solutions of this eigenvalue problem. He did not get even orthogonality relation correctly, but he was very close. At least he discussed properties of these eigenstates as a set of eigenstates. He was interested to investigate properties of these solutions as a set. He did not get, unfortunately, any results regarding completeness and orthogonality, but he indicated this problem. So now the first challenge which drove people's interest after paper by Siegert can be formulated as follows. Is it possible to reformulate scattering theory in terms of purely discrete set of Siegert states? Why this is interesting? Because in usual scattering theory, we usually have discrete spectrum and continuum spectrum. And it is always difficult to deal with continuum spectrum because if you do expansion in terms of a complete set of physical states, that means discrete state and continuum states, the continuum part is an integral, and an integral is always replaced by a sum of some discrete states in numerical calculation. That means you have any way to discretize continuum. Otherwise, you cannot do calculations. Meanwhile, Siegert states his eigenvalue problem suggested a purely discrete set of states, and the idea was probably it is possible to reformulate scattering theory in terms of this purely discrete set of states, and thus get rid of continuum from scattering theory. So this was motivation of a lot of studies which were conducted between the paper by Siegert in 1939 and my paper in 1997, which I will show later. So let me summarize now main achievements during these 60 years of the development of theory of Siegert states. So this is the Siegert eigenvalue problem. In that series of papers which I am now going to review, early studies, only this simplest scattering problem was considered. Potential has a finite range, central potential with a finite range, and S-wave scattering, so angular momentum is zero. Then the Siegert eigenvalue problem is formulated as follows. So it's a radial Schrödinger equation, a regularity boundary condition, outgoing wave boundary condition, and this energy appearing in the Schrödinger equation and this K appearing in the outgoing wave boundary condition are related by this, which I will call, and will return to this point later, uniformization transformation. From the point is that a problem is all functions, all objects appearing in this formulation in scattering theory are single-valued functions of K. But K is a double-valued function of energy. That's why in scattering theory, people usually talk about two-sheet Riemann surface of energy. One of the sheets is physical, the other is unphysical. But in terms of K, it becomes just one sheet, because K, in terms of K, these scattering states are single-valued functions, as well as scattering matrix, etc. So this eigenvalue problem defines a purely discrete set of states with energy and eigenfunctions. And outside the point A, where potential disappears, these eigenstates have the following behavior. And so it's purely outgoing. And if, since K, as I will show later, is generally complex, this exponent grows. This exponent grows, which means that the first problem you have to solve is how to normalize such states which exponentially grow as R goes to infinity. So this problem was first solved by, it doesn't matter method, but the correct result was first obtained by Zeldovich, but then it was obtained by many other authors. I mentioned Roma, who did a lot in this theory, by different methods. The simplest method was suggested, by the way, by Dechner, and it consists in the following. Let us use this form of the eigenfunction outside point A and integrate, so consider usual integral from 0 to infinity of two eigenfunctions. And the part of the integral from A to infinity can be calculated analytically, since we know analytical form of eigenfunctions outside A. Okay, eigenfunctions diverge. Then let's rotate the integration axis from A to infinity in the upper half complex R plane by an angle large enough to make, even if K is complex, to make the integrand decaying. So it's analytical continuation in R. And then you obtain this term as a result of integration from A to infinity. So the point here is that you cannot obtain this term staying on the real R axis, even though the function is known analytically, and this integral can be calculated analytically, but the function diverges at infinity. So you have to rotate, and then R goes to infinity, this limit does not contribute, and then this term comes from the R equal A. So this normalization, then this normalization condition, if you look at this term as the result obtained from integration from A to infinity, takes the usual form. Integral of two eigenfunctions gives Kronecker delta symbol. But there is one difference, still one difference there is. There is no star here. You see, both eigenfunctions are without star. And this is a very important point. The operation of taking complex conjugate is non-analytic. If your analysis is based on some analytic continuation, you cannot use this operation because it is not analytic. And as I said, as Dekhne suggested, this term appears indeed as a contribution from A to infinity through analytic continuation, and the trick would not work if there is a star. So this is a big difference from usual normalization condition, the absence of star, even though functions are complex. Now, so this establishes the orthonormalization condition for Siegert states. And the second important issue to be resolved to use these states as a complete set for expanding scattering theory is the question of what are the completeness properties of this set. And Roma was a mathematician. He published his papers in a journal of nuclear physics, but he was a mathematician. He derived these two relations. If you look at the second relation, it looks very similar to usual completeness relation for a set of eigenstates, except 2 here. The factor 2 here, one can say that, okay, let's renormalize phi and then get rid of these 2. But if you renormalize phi, then 2 appears here. These 2 cannot be eliminated from this equation. But then we have another relation. And this another relation shows that the set is overcomplete. Because some linear combination gives exactly 0. The set, these 2 relations establish some completeness properties, but they are very strange. They are very different from usual ones. First, because of these 2, and second, because the set is overcomplete. Linear combination of states is 0, which is impossible if the set would be simply complete. So this result was obtained in 1975, and these 2 together established unusual, but anyway, orthonormalization and completeness properties of this set. Let's go further. Now we are interested in the solution of this scattering problem. So the same radial Schrödinger equation, regularity boundary condition at r equals 0, and now usual scattering boundary condition at r goes to infinity, but here potential has a finite range. So at r larger than a, it should be incoming wave and outgoing wave, where S is a matrix element of the scattering matrix. And in this case, for this simplest scattering problem, it's just a phase factor with scattering phase in the exponent. The question is, we want to expand the solution of this scattering problem, which is a scattering state, in terms of Siegert states. This result was obtained by Serdoborsky, who worked in Lebedev Institute at that time in 1959. So this scattering state can be expanded in terms of Siegert state. Coefficients in the expansion have this form. And this applies for R from 0 to A, and for R larger than A, this formula applies. Now, scattering matrix. There are 2 kinds of results, expressions obtained for scattering matrix. The first one was obtained by Humboldt in 1952. It was his PhD thesis. He is from Belgium, as far as I remember. This formula expresses scattering matrix in terms of surface amplitudes. I call these values of Siegert eigenfunction at r equal a Siegert surface amplitudes. This formula expresses scattering matrix in terms of these Siegert surface amplitudes, and there is this resonance denominator. Now, the appearance of Breit-Wigner resonances is clear if one of Kn lies close to the real axis. Then when K, which is related to the energy, when K varies and passes through the one of Ka which lies sufficiently close to the real K axis, this is a resonance denominator. So this phase of this changes rapidly by pi, which is a signature of resonance. But there is another much more interesting expression for this S of K obtained by Hu, and then another approach by Riget. That Riget, whose name we know from Riget poles in also scattering theory. This representation for the scattering matrix requires only Siegert eigenvalues. It doesn't require any information of Siegert eigenfunction. That means about this surface amplitudes, which means, by the way, that surface amplitudes can be expanded in terms of eigenvalues only. And this is true, and I obtained this formula. It was not known that time. So you see, we have scattering state expanded in Siegert states. We have S matrix, even two different expressions for S matrix expanded in Siegert states. And then the most general object of the theory is Green's function, outgoing wave Green's function. It satisfies the same Schrödinger. Oh, I'm sorry. Here should be delta function, of course, just delta r minus r prime. It satisfies regularity boundary condition, outgoing wave boundary condition, and Moore and Gerjoy obtained this formula for the Green function. Actually, having this formula, this, for example, is easy to obtain. And also this is easy to obtain. This is different. So let me say a few words. So this is the complete set of results in the theory of Siegert states available before I started to work in this direction. And let me just mention the tools, mathematical tools used to obtain these results. Two major tools are Mittag-Lefler expansion theorem and Weierstrass factorization theorem. Let me comment here about these theorems. If you have a rational function, which means that a function given by a ratio of two polynomials of finite order, it is quite clear that you can expand this function in elementary fractions. Each fraction has a pole in a certain point, and the number of such pole terms or elementary fractions is finite, equal to the number of to the order of polynomial in the denominator. But the same expansion or similar expansion in terms of poles can be obtained, and this is the Mittag-Lefler expansion theorem, for an arbitrary meromorphic function. Meromorphic means that this function has no other singularities except of poles in any finite part of a complex plane. So meromorphic function can be expanded in terms of its poles. This requires to know position of poles and residues at the poles. And then you can expand meromorphic function, unfortunately, up to an entire function, up to a factor given by an entire function. This expansion, this theorem gives this. You see here, what is in square brackets is a function of k expanded in terms of its poles. Poles are located at kn, and this coefficient together gives a residue at the pole. But there is an entire factor in front of the whole of this construction, and this entire factor Mittag-Lefler expansion theorem does not predict. So actually the contribution of these people who derived this formula was to obtain the residue in terms of Siegert states, but also to figure out what is the entire factor, because this theorem does not predict the entire factor. And what is Weierstrass factorization theorem? If we have a polynomial, we know of finite order. We know that we can factorize it into factors, each of which tend to zero at one point, maybe powers of these factors. But the same factorization applies to an entire function. Entire means that it does not have any singularities in any finite part of complex plane. That means it usually has singularity at infinity, and if it has a pole in infinity, it is a polynomial, and if it has an essential singularity in infinity, for example, this is exponential function, has this property. So a function, an entire function can be factorized in terms of its zeros. But again, up to an unknown entire function factor. So here, this formula comes from this Weierstrass theorem applied to so-called Yost function. So here, zeros of Yost function and zeros of Yost function of minus argument, and this is the entire factor which is not predicted by the Weierstrass theorem. So methods used to derive these results were based on essentially on these two theorems, and let me call them analytical methods. Analytical means not derived analytically by hand, but it means that they are based, the application of these methods are based on some analytical properties of the object which we consider, for example, S matrix or scattering state or green function as a function of K, complex K. This is the summary of results available by the time when I became interested in this. So the next challenge is the main defect of what was available is twofold. Two major problems can be indicated in what was available. First, this is extremely simple scattering problem. From to apply this methodology to some realistic scattering system, the problem must be generalized. At least angular momentum must be incorporated, non-zero, and to three-dimensional case, etc. So how to generalize these results to more realistic scattering problems? Yes, please.
Nice. But what about negative with Levinson theorem? Are you still going to keep positive potential?
No, you mean negative n eigenvalues?
No, negative V. You put at the
arbitrary, V arbitrary.
But in previous page you were saying that the formalism was for S state and V bigger than zero.
No. I didn't say this, or maybe I said
one,
this by
yes.
mistake. No, V is arbitrary.
V of R
usual potential which we meet in scattering
cut
theory.
off, but it could be
value.
negative as well. Yes.
Yes, negative, positive. It may have bound states. It may have resonances. It has...
Do you do because kind of we from textbooks are familiar with scattering phase shifts and things like that, and theorems when
Levinson theorem
approaches
V
zero.
is general V for which Levinson theorem applies, for example.
Okay, and another one because you also cut at finite A. What about there is a Scala-Jera Babikov variable phase method.
Yeah.
Is it crucially different?
Absolutely. Phase method eventually is based on approximation, semi-classical approximation.
No,
you can solve these equations exactly for phase.
Yeah.
But what
for phase
people
shift,
usually do in that direction, why those equations for phase are useful? Because
I think it's just to reduce to first order nonlinear from second. It's numerical thing from second order equation to first order for the phase.
Then I say this way: that method does not lead to this complete and orthogonal set of states.
Okay, thank you. Then finally, a lot of us here do with 2D, and at small distances, it is kind of logarithmic solutions which are non-analytic. Does your stuff has anyone reapplied that methodology to 2D?
Yes, but it's not these results. It's results which I'm going to discuss next.
Later. Okay. Thank you very much. I'm sorry for interrupting.
No, it's very good. And you mentioned something about cutoff. Since you mentioned this, let me say the following. All these results, analytical results obtained by these authors, apply only to the case when this potential indeed strictly disappears beyond certain radius. So it's finite range potential. If we consider potentials, the question is for which, how fast these potentials should decay for these results to be valid for infinite range potential, but quickly decaying. The
faster
answer
than
is
1
that these
over R
analytical
squared.
properties hold for potentials decaying faster than any exponential function.
Exponential.
Any
so,
exponential function.
Power
Exponential
is
itself is not enough.
I see.
For if this potential is purely exponent, there are so-called redundant poles.
That's why you said screened. Now I
Yes.
understand.
Yes.
Yeah, okay. Cool.
Now my motivation was twofold, as I said. And first, to generalize just the scattering problem treated in what I showed previously, to generalize to such a level that is applicable for dealing with realistic scattering problems which we meet in physics. How to generalize? That means, of course, dimension.
To break in again. But then in 2D, you do not screen exponentially. You screen over 1 over r cube, like dipole with
Okay,
the
let's
gathers.
return to this point later. Then it's
Later,
only
sorry.
by convergence. It's doable, theory is applicable, but then you have to increase this A, cut off at some A, and see what happens with the results when A grows. So, and second problem of the previous results is that nobody have ever implemented them in calculations. These results were available in such a nice analytical form, but no one, people tried, but it's not clear how to solve this eigenvalue problem to generate a set. You can solve this eigenvalue problem and find one solution which corresponds to some particular resonance, scattering resonance, maybe 2, maybe 5. But you cannot generate a complete set using which you can. So these results have never been implemented numerically. So these two major problems of the previous formulations were resolved in this paper. So I will discuss briefly, not briefly, in more details, because this is very simple, what was done there, and then I will give less mathematical details. So let's consider finite basis defined in the interval from 0 to a and orthonormal in this interval. And this basis becomes complete if number of basis functions goes to infinity. Let's expand the solution of Siegert eigenvalue problem in terms of this finite basis. Finiteness of the basis is essential. This is the difference between Siegert states and Siegert pseudo-states. The term introduced here. This is the Siegert eigenvalue problem. Let's multiply the Schrödinger equation from the left by one basis function and substitute here for phi this expansion. When you multiply it from the left and integrate from 0 to a, treating this second derivative term will give you, integrating by parts, this second derivative term will give you first this term, which is hermitized Hamiltonian. But in addition, it gives, integrating by parts, gives surface substitution. But due to this boundary condition, this surface term is proportional to ik. So in matrix form, which incorporates this boundary condition, this equation for the coefficients in the expansion take this form. Here, H with tilde is hermitized Hamiltonian. L is a matrix given by surface amplitudes of the basis functions, and this is the unity matrix. Let me name the properties of these matrices, which are important, and all results will follow from these properties. This is real symmetric. We assume that basis is real, so this matrix, hermitized Hamiltonian, is real symmetric. This matrix has a very special property. Its rank is 1. So it has only one non-zero eigenvalue. Because it's...
Yes. If M is finite, then pi E is not complete, right?
Yes. For any finite N, it's not complete basis.
Then how we can expand pi?
Yeah, I just look for a solution. So I cast this differential equation into matrix form. I didn't say that I find the solution. I just let me substitute this here, multiply it from the left on the another basis function, integrate. I obtain this matrix equation. I am now discussing the properties of this matrix equation. So actually the solution of this matrix equation will be called Siegert pseudo-states, and this is the key point in the whole story. Okay, let me continue. So this is real matrix. and symmetric. This has rank 1. Rank 1 means that one non-zero eigenvalue. You see it's a direct product of two vectors. And this is unity. This matrix equation should be solved with respect to k. K is the eigenvalue. And you see that this is unusual eigenvalue problem is quadratic in k. Eigenvalue appears here as k, but also as k square. And we can do the following trick. This quadratic eigenvalue problem can be linearized. If we we extend our Hilbert space of vectors which are composed of the coefficients in this expansion, vectors of length n, we extend this space twice by adding another component of length n given by ikc. C is the upper component. And for such a combined vector of dimension 2 times n, this quadratic eigenvalue problem takes this linear form. Now, k eigenvalue appears as it should just in the first power, but there is some weight matrix. And this is the matrix whose eigenvalue with such a weight must be found. But this linear algebra, we know everything about linear algebra. So all the properties of the eigenvectors of this equation can be derived very simply from linear algebra. For example, if we solve this generalized eigenvalue problem, why generalized? Because there is a weight. Usually in usual eigenvalue problem is matrix times vector is number times vector, eigenvalue. But here it's weight. So since there is a weight, the eigenvectors are orthonormal in this way, with respect to this weight. These eigenvectors belong to a space of double dimension, 2 times n. And they are orthonormal, as usual in linear algebra, with this weight. But when you now cast this equation, reduce this equation into to eliminate this c tilde and write what does this mean with respect to these vectors, you obtain this. Now, if you return to coordinate representation, you obtain this, which was shown previously as a result of orthonormalization condition for Siegert states. And the second important thing, set of eigenvectors of this generalized eigenvalue problem, of course, constitute a complete set in the space of dimension 2 times n. But this completeness relation has this form. On the right, we have not unity matrix, but this inverse of the weight matrix. This is the inverse of this matrix. But this is just ordinary completeness relation in a finite dimension vector space for finite dimensional linear algebraic eigenvalue problem. Now, on the left, you have matrix, block matrix 2 by 2, and on the right, 2 by 2. So you can write 4 equations of dimension n. Here, matrix has dimension 2 times n by 2 times n, and here 2 times n by 2 times n. Now I want to equate blocks, this block with here, this block with here, etc. But this matrix is symmetric, so 3 equations appear. This means that we calculated this product and took the left upper element and equate it to 0. This means that we equate to 1, but there is one more equation which gives from this comes from this bottom right corner. So these 3 sets of relations for this eigenvector C follows from this completeness relation in the extended space of dimension 2 times n. When we come back to space of dimension n, we obtain these 3. Now, in coordinate representation, they become... So these 2, you can recognize are results obtained previously by previous authors. But there is one more, which is new and not known previously, but it does not add much. It just shows again that the set is overcomplete. But now all these results follow immediately from just linear algebra and properties of this L operator. So I do not show how to derive results which all these formulas can be now derived within this algebraic formulation. I skip this derivation because I think these details are not needed for the talk, but all these formulas can be derived and in a very simple way, algebraically, using the properties of the matrix which I mentioned before. This is symmetric and this is has rank 1. That's it. Now, the most important point about this, before we come to some results, illustrating results. Why this term is introduced? Because all these properties, orthonormalization, completeness, and all the equations defining S matrix, green function, and scattering state hold for any finite n. They hold algebraically for any finite n. Now, big N, number of basis states. So they are just some algebraic relations which hold for any, even n equal 5. They hold for n equal 5. Now, if n becomes infinite and this completeness works, then solution obtained from this formula reproduces exact solution of Siegert eigenvalue problem. But all these equations hold for any finite n. So we don't, that means we fix n, obtain easily using, solving this eigenvalue problem, linear algebraic eigenvalue problem, obtain the set of Siegert states, finite set. There are 2 times n solutions. Using this 2 times n solution, calculate this matrix, green function, etc. And these results reproduce the exact results within some interval of k. And the width of this interval depends on n. If n grows, the width grows. So simple example showing how it works. So the very basic, simplest potential is just rectangular potential. Rectangular potential, yeah, here I'm now discussing a series of 4 papers entitled Siegert pseudo-states formulation of scattering theory with different extensions. So this is the simplest one-channel case. Here I still consider the same S-wave scattering in a finite range potential. As the simplest finite range potential, I consider rectangular potential. So for this rectangular potential, the set of Siegert pseudo-states is shown here. And here the properties of Siegert eigenvalues are listed. Siegert eigenvalues can appear in complex K-plane either on the imaginary, positive imaginary axis, and then they represent bound states, either on the negative imaginary axis, then they represent anti-bound states. And then there are sequences of solutions going like this to infinity, but for any finite n finite sequences, but when n grows, they go to infinity. And they appear in pairs. For each kn from here, there is minus kn star here. So among among this sequence, there may appear a root which lies close to the real axis. This root will represent a resonance state. If you look at this figure in the energy domain, it looks like this. The right column shows similar results for a potential supporting one shape resonance, and this potential is often considered in these resonance calculations. So this potential, these are Siegert eigenvalues in the complex K plane, and you see they form some sequence. This potential does not have bound states, so there are no roots on the positive imaginary axis, as well as no roots on the negative imaginary axis. Siegert states form some sequences going to infinity, and there is one root which lies separately near the real k-axis, a little bit below real k-axis, and this root represents this shape resonance. And in the energy domain, it appears somewhere here. So having these roots, we can calculate all the objects shown previously: scattering matrix, scattering state, green function, using some algebraic formulas which I skip here. And now I jump to most ambitious application of this approach. This is this is true three-body Coulomb problem. Three particles in 3D. Particles are two electrons and a proton with finite mass, by the way. And we consider this system in 3D, I repeat. And this shows a distribution of Siegert eigenvalues in the energy plane. And this increases this part of the plot. So here we have one bound state. This system is called hydrogen minus. So it's negative ion of hydrogen. This hydrogen minus has indeed one bound state. It's shown by the pole here. And then it has this discretized continuum. But here, if we look more carefully here, we can see there are no second bound state, but this second bound state appears as a resonance below n equal 2 threshold. And then there are resonances below n equal 3 threshold, and they appear as separately lying points here. Now, having this set of Siegert eigenvalues and using those simple algebraic relations which I showed before, we can do the following. The set of eigenvalues include bound states. If we talk about H minus, these two values show the energy of the only bound state of H minus. These results were obtained by the best available variational calculations. Variational calculations usually give very good energy of bound states. And these results are obtained by this Siegert pseudo-state calculation, so they are very close. Now, the same approach is applied to dt mu. Dt mu is an exotic three-body Coulomb system, which is very important for muonic catalysis. And some time ago, I worked on three-body Coulomb problem, and for me, all these systems were a playground where I applied my theoretical methods. So this dt mu, also bound states in this dt mu were calculated, and this very nicely agree with what is obtained by this method. This is about bound states. Now about resonances. In H minus, we have this n equal 2 resonance, which has been calculated previously by many authors. So resonance means you have to calculate energy position and energy width, gamma, resonance width. So different methods shown here: convariational, Feshbach formalism, complex rotation, and this Siegert pseudo-state with finite mass, proton mass, and infinite proton mass. Okay, they nicely agree with best available variational results. This is about H minus. Now about dt mu. In dt mu, we have similar resonances, and they play actually a very important role in muon catalysis, because catalysis, that means capture of muon, which catalyzes DNT nuclear reaction, occurs through this resonance state. And it was predicted that one muon during its lifetime can catalyze more than 100 nuclear reactions, which if this would be true, this would be a very promising system for energetics in the future. So this complex, this resonance was calculated by variational method, which gives only real part of its energy, then complex rotation method, which gives real part and width, another complex by other group also width, and this is present. And you see present width are 3-5 orders of magnitude smaller than was predicted by previous authors, and later these results were confirmed. So this method turned out to be even more accurate than all this complex rotation. And so these bound states, resonances, and now scattering phase in electron hydrogen scattering. I repeat, this is three-body Coulomb problem, so it's six-dimensional problem.
So this difference in several orders just because of exponential?
No, this is correct. My results.
I mean, because gamma is related to exponential placings with a barrier, tunneling. I mean. Why?
You mean the mechanism of decay of this? No, it's not tunneling. It's Feshbach resonance. It's if you have two channels coupled, and the upper channel has a potential well, and there is a state bound in the upper channel, but it decays through non-adiabatic coupling to the lower channel. This is called Feshbach resonance. It's not tunneling, but those resonances are very narrow, and this method, complex rotation, failed to reproduce width. And now elastic scattering of electron by hydrogen. I repeat, this is six-dimensional problem. But L equals 0, so it's again three-dimensional problem. Total L is equal 0. This is a test ground for most advanced methods in the three-body Coulomb problem. And as far as I remember, these 23 are results by Schwartz, which are considered the best for scattering phase in this scattering. And here results for infinite proton mass and finite proton mass obtained by this Siegert pseudo-state method. And all this illustrates the following. Siegert pseudo-states, these eigenvalues include all states observable or having physical meaning individually, bound states, resonances. In addition, it includes a infinite set of complex energy states, which all together with bound states and resonances can be used to describe continuum. So all features, bound states, resonances, and continuum can be reproduced by this method. And this version of the theory, immediately after it was published, many people started to use this theory in its simplest version, which I showed so far. And many papers, now more than 100 papers use these results from Siegert pseudo-states. This is one of the first where I was not a co-author. I know these people, but they did this themselves. So they considered dissociative photoionization of H2 plus ion. So when electron is detached by absorbing a photon, two nuclei dissociate naturally. So they calculated this Siegert pseudo-state for this system, and applying formulas, algebraic formulas using this Siegert pseudo-state, they obtained this dissociative photoionization cross-section. I don't show details how they did, but this is the scenario of many applications of this method in different realistic collision problems. Now I go next to generalizations of this theory. So second paper in this series, Siegert pseudo-state formulation of scattering theory, considered two-channel problem. Let me check. It's almost over. Okay, then probably I skip. Maybe only I show this briefly. Here, to treat matrix potential, we need a new uniformization variable. Uniformization variable which makes scattering problem, which is in this case four-valued function of energy, which makes it a single-valued function of uniformization variable. Because k is double-valued function of energy, but there are two different k now. So this uniformization variable can be found. This is given by these equations. This is the plane of this uniformization variable. Instead of k, now you have to treat this u. Physical sheet is what lies on the right of this semicircle. So there are four sheets, as you can see here. Physical sheet is here, and first continuum here, and second continuum here. Okay. You can find resonances, and they are reproduced in scattering. And then another generalization to non-zero angular momentum. This outgoing wave boundary condition, if L more than 0, can be generalized this way. This exact outgoing wave boundary condition that Hankel of the first order satisfies. This is so-called Bessel polynomial. Hankel is outside R equal A, outgoing wave. It satisfies this outgoing wave boundary condition. Then again, the whole problem can be formulated, reduced to pure linear algebra, and a lot of resonances in scattering can be described. And eventually 3D generalization. Here I considered like Yukawa potential, but this is supposed to be, electron is supposed to be in a crystal, and with different anisotropic mass, three different values of mass with respect to the three different axes. And here, differential cross-section on such a potential. Here is the set of Siegert states. So theory is generalized to 3D case. Okay, then there is a series of papers where Siegert state expansion is used for solving non-stationary systems. And this involves a very interesting object, square root of d over dt. It's pseudo-differential operator. And introducing this pseudo-differential operator, you can factorize this Schrödinger equation and present it in such a matrix form by doubling the dimension of Hilbert space. And then this matrix is exactly the matrix that appears in the Siegert eigenvalue problem. So you can expand this in terms of Siegert states and obtain the coupled equation for the coefficients. They're pseudo-differential equation because this is the square root of d over dt. And this works very efficiently, and some physical effects like rapid doubling in continuum was predicted using this approach. And then I derived, if potential varies slowly with time, we can switch from diabatic basis to adiabatic basis and obtain generalized Bohr-Fock equations. Why this is needed? Because then you can derive analytical formula describing non-adiabatic transition to continuum. Now continuum is a set of discrete Siegert states. And you can derive an analytical formula describing non-adiabatic transition to continuum. And this shows how it works. The solid line is the formula, and dots are numerical solution of some problem. Okay, and 3D case eventually. And then not done yet, not completed yet, whether theory can be expanded to include an external electric field. And in some sense, yes. But then you have to treat static field induced states. And static field induced states produce this rapid rising of scattering phase by not pi, but something non-negligible when energy passes through this static field induced states, which is one of Siegert states now. And in 3D, these static field induced states were analyzed, and this semi-classical quantization condition was derived. So we know now a lot about the static field induced states, but unfortunately, we still don't have the orthogonality and completeness relation for them. That is why we still cannot formulate scattering theory in the presence of an external static field. So this is the current state of the theory. That's it.
Okay, let's. So questions, the audience?
Yeah, please.
No, first I
okay.
to ask. So I didn't get how do we obtain discrete set of eigenstates, Siegert eigenstates, with this outgoing boundary condition? How do we know that?
It's purely discrete.
Yes, yes.
Okay. Now, I prefer to divide the analytical approach presented here and here from the Siegert pseudo-state algebraic approach, which I developed myself. So in analytical approach, everything is very difficult. To prove this, any of this formula requires a lot of mathematics, and these people, Romans,
because I thought
yeah. So I prefer do not comment on how discreteness of the set of Siegert states can be derived within analytical approach, but within algebraic approach, it's trivial. It's just a solution of this algebraic eigenvalue problem whose dimension is 2 times n by 2 times n. That's it. You solve this, you call Laplace, you solve these equations, obtain 2 times n states, and insert them into given formulas. That's it.
Okay.
Yeah, please.
Misha.
I mean, I stumbled several times, and in this slide particular. So you have this unusual normalization condition with 2. Can
Yes.
you give an example of function or explain any physical meaning? In your stuff, it's also with 2. And in, you explain that when they are not, that there is no condition on function product complex conjugate, but without complex conjugate, it has to be 2 delta functions.
Yes.
So is there any mathematical reason, real parts double?
Yeah, doubling of Hilbert space, this is the point. 2 looks unusual if you stay in the space of functions satisfying this equation, that's it. But it is not enough. If you double the dimension, you are in different space. And this is the projection of the usual, very simple normalization and completeness relation in the space of double dimension to the original Hilbert space. That is why 2 appears. And this kind of relation appears, which shows over completeness of the set.
Mhm.
In the usual sense, set is strange, over complete, 2. But in the double space, these two conditions are trivially consequences of this algebraic eigenvalue problem.
Can, like for the problems that we know the solution exactly. For
Yeah,
example,
rectangular
three-dimensional
potential,
hard
for
sphere.
rectangular potential.
Да, rectangular
Yes,
potential,
yes,
yes.
everything is known.
For pi, everything comes back to doubling the cross section or something like that.
Doubling cross section.
No, I mean for S state in
Yeah.
a solid sphere,
Yeah.
it's known that the answer of the cross section, total cross section, is
No, I don't think I
4
don't think this is related to
pi
that.
radius squared. Can I get that answer?
Yeah, I know, but I don't think that these two in completeness relation is related to that two which you mentioned.
No, I don't relate the twos, but I'm just checking. Did you check your formalism on?
Yeah, of course. I show here only a set of Siegert states, but using formulas like this, but expressed in terms of these Siegert pseudo states, I reproduce scattering characteristics in the paper. All scattering,
Yeah, okay.
cross-section, phase, everything. Of course, this is the point. I just skip this because these formulas are all correct. The question was how to implement them. Now I know how to implement them. And they all follow from this formulation using just two properties of these two matrices. This is rank 1 and this is symmetric. That's it. All these equations for scattering, formulas for scattering matrix, green function are derived.
Thank you.
If we don't have,
I have a question. Why is 5 incomplete, overcomplete?
Because you see, suppose phi is usual complete set here, unity. Unity doesn't matter in this sense. But what does this mean? Phi of r prime over kn are some coefficients, and phi of r combined together with these coefficients gives 0. That means this phi is over complete. Yeah. There is a linear combination because it is over complete in the original Hilbert space. But in the space of double dimension, it is just complete.
If you do not use the double.
If you don't know, then all these properties look for you very strange. Completeness and orthogonality relation, if you don't know that you should look at them from the space of double dimension, then these properties look very strange to you. That is why it took 60 years to derive these results. To derive these results analytically, staying within original Hilbert space, it was very difficult. It took 60 years. But when you switch to the space of double dimension through this operation, then all these relations become trivial consequences of this algebraic eigenvalue problem, whose dimension is twice the original basis.
So if phi is degenerate, can you distinguish two degenerate phi?
Phi is degenerate, but this vector is not degenerate. Yeah. Lower component of this vector is just upper component times kn. Yeah, but the set of these vectors, 2 times n of them, this set is usual orthonormal complete set. When you project onto the space of reduced dimensionality, 1/2, then you see that the set is over complete. And some interesting another relation appears.
Basically, K is different.
Huh?
Degenerate comes from K.
From reducing a total number of linearly independent states is 2 times n, but when you reduce to the space of dimension n, they become degenerate.
we don't have, then
Okay.
I was speaking. Very interesting.
Профессиональный человек.
Неописанные квантовые физики.
Да.
Дуальный базис. Вводится функция
Я
для
думаю, что это то и есть.
Гамильтониана и для методосопряженного Гамильтониана.
Это
Два типа.
Это не то.
И тогда можно восстановить обычное скалярное произведение.
Нет, возможно и то. Это возможно,
это просто...
возможно, это связано как-то. Но, понимаете, то, что вы говорите, оно известно давно. А вот в этой теории вот эти вот соотношения ортогональности и полноты, эти математики.
Ну, то, что я говорю, это, по-моему, было введено только...
Все, до свидания всем.
Ну, тогда, возможно, и... Понимаете, те люди не знали этого. Вот классики, так сказать, кого я упоминал.